All right, we'll get started. I'm happy to introduce Kat Davidson. Um, she did her undergraduate at Auburn and her PhD at University of Alabama, Huntsville, and is now a postdoc at Boston University. Um, we met because we were in a peer mentoring circle, is that what it's called? That was set up by Jim during AGU this past December, and we were put together in that. I said, hey, I'm doing a career just down the road. So
The peer circles worked.
yeah, good outcome from those. So yeah, she jumped on the train this morning, and here she is. So take it away.
Okay, thank you. Yeah, thanks for the introduction. Yeah, again, Kat Davidson, postdoc at Boston University, working with Toshi. Today I'm going to be talking about investigating magnetosphere-ionosphere coupling sequences through ionospheric flows. So first, just to introduce magnetosphere-ionosphere coupling, this is the connection between the magnetosphere and the ionosphere through equipotential field lines from Earth's magnetic field. And the most famous example of magnetosphere-ionosphere coupling is the Dungy convection cycle. So this occurs when you have a southward IMF, and this connects with the day-side magnetosphere here. These newly opened field lines then move back towards the magnetotail, where they squish and connect again, sending those tail lines or magnetic field lines back to the day side. And so this whole process is mapped to the ionosphere through this magnetosphere-ionosphere coupling. And so in the ionosphere, what this will look like is a anti-sunward motion over the poles. So this anti-sunward motion is reflecting this tailward motion of the field lines. And then a sunward return flow over the dusk and dawn side. And that's representing this return of the field lines back to the day side. This, in the ionosphere, it's a two-cell convection pattern. So again, you have anti-sunward over the poles and sunward on the auroral zones or the dusk and dawn side. And this convection cycle actually can vary a lot depending on the IMF conditions, these solar wind conditions. So it's stronger during a southward IMF, that's when you get your reconnection. And it can also rotate clockwise or counterclockwise based on the dawn-dusk direction of the IMF as well. And so I say that just to say that the stereotypical two-cell picture, large-scale picture, is not what is always happening, and we can talk about that a little bit more later. So I say we are using ionospheric flows to investigate magnetosphere-ionosphere coupling. In order to do that, we actually use ionospheric flow channels to get a view into the magnetosphere. So these flow channels that we see in the ionosphere are actually representing flows in the magnetosphere. Because of the coupling, once again, these flow channels are mapped down to the magnetosphere, giving us a sort of telescope into what's happening there. The best example of this are bursty bulk flows. So bursty bulk flows are earthward flows in the magnetotail that are very narrow and fast. You can see on the left figure here, this narrow burst of flow in the magnetosphere going towards Earth. And what that looks like in the ionosphere is a streamer. So this is a north-south aligned arc, as you can see in the auroral image here. And accompanying that streamer is an equatorward flow channel that's seen in this red burst of flows from radar data here. So an equatorward flow channel maps down into the magnetosphere as an earthward flow channel. So these equatorward flow channels associated with the streamers are known as mesoscale flows. So these mesoscale flows are varying from the large-scale convection pattern that we saw in the previous slide, but these mesoscale flows are still embedded in that overall large-scale pattern. And these mesoscale flows are actually very important for transporting energy throughout the magnetosphere. They make up over 60% of the earthward magnetic flux. So we are using those flows to investigate the different dynamics happening in the magnetotail. One of those dynamics that we're looking at is a poleward boundary intensification. So these are brightenings or intensifications of the poleward boundary. It's kind of intuitive there. So this figure on the right shows image satellite data of the auroral oval. And you can see these brightenings along the poleward boundary here. And there's one there, one there, one there. And those are PBIs, brightenings of the poleward boundary. These PBIs are longitudinally localized, so again, happening on that mesoscale phenomena that we're talking about. And these PBIs have been observed simultaneously with tail reconnection signatures. So that leads a lot of people to believe that these PBIs are actually signatures of the reconnection X line in the tail. And this marks the entry of plasma into the magnetotail from the solar wind. So it's very important to study the dynamics of these PBIs because they are telling us how plasma is entering into the magnetotail through reconnection. The next dynamic that we're talking about are going to be substorms. These are explosive releases of stored energy from the magnetotail into the high latitude ionosphere. They were first characterized by auroral signatures as an auroral brightening, initial brightening on the equatorward edge of the auroral oval. So you can see by this darker line here, that's your brightening. And then a subsequent poleward and westward expansion of the auroral oval here. So these substorms also are reconfiguring the tail magnetic field. So in addition to the auroral signatures, we get a dipolarization of the magnetic field. And so we want to investigate what kind of dynamics are causing these substorms and causing this global reconfiguration of the magnetic field. Despite how important they are, there's a lot of debate on how they're triggered and how the expansion is fueled. Two of the most prominent theories are the outside in and inside out model for triggering. Both of these models use the same phenomenon as such as a tail reconnection event and a current disruption in the inner magnetosphere, but it just differs on how these are ordered. So outside in has the tail reconnection first, inside out has the tail reconnection last. And it's still up to debate on which one of these models are the most dominant. There's a new proposed onset sequence, which was introduced by Toshi back in 2010. This is a substorm triggering by new plasma intrusion. So this sequence includes a poleward boundary intensification here. This PBI extends into a streamer or north-south aligned arc and approaches this growth phase arc. Once the streamer reaches the growth phase arc, it triggers onset and the ensuing expansion. And again, relating this to the magnetotail, this is indication of a bursty bulk flow along with that streamer, moving earthward from the tail and delivering low entropy plasma to the near Earth plasma sheet. And once that streamer is delivering the low entropy plasma, you get a pressure gradient instability and triggers instability leading to onset there. The sequence has primarily only been investigated using ASI images, like the study here on the right. And so now that we have high resolution ionospheric flow channels, we can start to investigate each part of this sequence using ionospheric flows. So the first step in the sequence was a PBI. So first looking at the relationship between PBIs and flow channels. Flow channels or flow bursts are commonly observed up to 90% with PBIs. This is an indication that we're having inflow coming in towards the reconnection site and driving tail reconnection. And this figure on the right shows ASI images, just auroral images of the aurora. And the SuperDAR radar data overlaid on top of it. And you can see this flow burst coming in as this teal narrow channel of flow. And that's about 2 minutes before the initiation of a PBI here. So this is kind of what we're referring to when we see this flow burst triggering PBIs. Now, again, PBIs and the associated flow structures can reveal X-line dynamics because we are trying to use these ionospheric signatures and ionospheric flows to study the dynamics in the tail. And with PBIs being the signature of X lines, we can then start to parse out that information there. So one of the things we're interested in are multiple PBIs. This could be an indication of multiple X lines. So as you can see in this figure here, we have 3 PBIs along the poleward boundary. This could be an indication of 3 different X lines in the cross-tail direction. We're also interested in the longitudinal extension of PBIs. This could be a signature of the X line spreading, again, in the cross-tail direction. And this figure here shows an east-west cut of an auroral image. So when you see this spread in the y-axis here, you're seeing a spread in the cross-tail direction of the PBI. Again, probably corresponding to the spreading of an X line. As you can see in the top right, previous studies of PBIs and flow bursts just use line of sight data, and there hasn't been any two-dimensional flow structure characterized around them. So that's something that we are interested in doing today. The next step of the substorm triggering sequence is onset. And so again, the proposed sequence has a streamer coming towards the onset arc and triggering onset. What this should be is an equatorward flow accompanying the streamer approaching the growth phase arc. Again, this equatorward flow is related to a bursty bulk flow or maps to a bursty bulk flow that's delivering low entropy plasma to the near Earth plasma sheet and triggering the instability there needed for onset. These figures here show the all-sky images, again, with the aurora in this white light here. And these flows on the bottom are high-resolution flows combined with a background convection model. And in the first panel, you can see that the flows are starting to diverge toward this growth phase arc. In the second panel, you have these flows reaching the onset arc and triggering onset. And the flows continue toward the surge, fueling that expansion. So this is just one study using high resolution flows studying substorm onset. So that's something that we definitely need more evidence of. And there's also not a very clear picture of what controls the duration and expansion of the size and duration of substorm expansion. However, this might also be related to the flows. So recent studies have shown that flow channels will feed a westward traveling surge. As you can see in this figure here, again, ASI images, just the aurora in white light. And this is Pfizer line of sight data. And you can see this is the surge associated with a substorm expansion phase. And for each step of this surge, we get an enhancement of the flows towards the surge. So this suggests that the substorm expansion size and duration might also be related to these incoming flow channels. And again, just more evidence with two-dimensional flow characterization is really needed there. So that brings us to our motivation. We want to determine the influence of ionospheric flow channels on the spatial extent and number of PBIs. Again, by studying the PBIs, we're also revealing the triggering spatial extent and number of tail reconnection X lines. And we also want to determine the influence of intruding ionospheric flow channels on substorm onset location and determine the role of ionospheric flow channels on substorm expansion. And by doing both of those things, we're revealing what magnetotail dynamics trigger substorm onset and contribute to expansion, and how the flow channels play a role in all of that. So in order to do that, we're going to be using super darn high frequency radars. These provide line of sight plasma velocities. And we're also going to be using Themis all-sky imagers and T-Rex all-sky imagers to provide auroral observations. These are just cameras that observe the aurora, so they're very simple data sets to use. And both of these data sets have a very large overlapping field of view over northern Canada and Alaska. And this allows for coordinated investigations of both the auroral phenomenon, such as substorms and PBIs, and the high resolution flows. So the super darn radars provide line of sight velocities, and we need to transform those to two-dimensional flows. The original method for doing this is using a spherical harmonic fit technique. This technique combines the line of sight velocity data that's obtained over a grid from SuperDARM, like the one on the left figure there. It combines it with an empirical model to kind of fill in all the gaps from the data, and then uses an 8th order spherical harmonic fit to give a spatial resolution of around 3 MLT. So this kind of prevents the resolution of smaller scale sizes and just gives the large scale convection cycle, as I showed in the very first slide. So this is the resulting spherical harmonic fit data of this event here, and you can see just the large scale 2-cell convection pattern there. So in order to see smaller scale sizes and resolve the mesoscale ionospheric flows, we use a new application of the spherical elementary current systems method. And this gives us a resolution of around 50 kilometers, which is much better than the spherical harmonic fit data and allows us to investigate mesoscale flows. This method utilizes the divergence-free condition of ionospheric flows. So instead of solving for the divergence-free condition by itself, it actually places poles of divergence-free flow around the regions of SuperDARM echolocations. And that results in this matrix equation here where Z is your line of sight velocity data from the radar. I is your pole of divergence-free flow. And then the transformation matrix T just converts your pole of divergence-free flow to the line of sight data. And then you do a singular value decomposition to get I, which gives the flow vector in the bottom equation here. In addition to being high resolution, this is also a completely data-driven method. It doesn't use any background models to fill in any data gaps. So it's true data, true high resolution flows. So to look at a comparison between the spherical harmonic fit data and the current systems data, this figure here shows a line of sight data from the SuperDARM radars. And in this figure, you can see several flow channels just from the line of sight data alone. You can see an individual flow channel here, 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 and these flow channels are identified just as enhanced flows from the background. So these reddish areas are identified as flow channels. And the spherical harmonic fit results are shown in the second panel here, and you can see just these large scale two convection patterns from the resulting fit. So we don't maintain any of these individual flow channels when we apply the spherical harmonic fit technique. The bottom left panel shows a combination of the high resolution flows and background model, just like the substorm onset slide, and it is mostly still just the large scale convection pattern. You have some flow channels here, but it's not resolved very well. And then the bottom right panel shows the spherical elementary current systems method. And you can see that we maintain all of these individual flow bursts, like here, here, and here. But it still resembles that large scale picture. So we still have these little mesoscale bursts within the large scale picture. And that makes this method suitable for studying our mesoscale ionospheric flows. So again, going into the first step of that sequence are PBIs. So we're just going to take a look at 3 different PBI events and how they relate to the ionospheric flow channels. These videos here show the all-sky image data in this grayscale image here, and then the bright portions of the aurora, except for this, that's the moon. And then the resulting high-resolution flows are overlaid as these colored arrows here. The thicker arrows indicate regions with super dark echo coverage, so high reliability for the solution there. This was a quiet time event, as you can see, by very low IMF driving, quiet SMH, which is a measure of the storm index, and then quiet SME index, which is a measure of substorm activity. So not too much activity going on for this event. What we will see in the video is that the PBI and the flow channel both extend westward at the same time. So, oh no. I think if I turn off the laser pointer, there we go. Okay. All right. So there we see our flow burst coming in there. And immediately after the flow burst, we get a PBI. The PBI begins to extend westward, now taking over the whole longitudinal extent of the camera. And you can see the flow channel has also widened significantly to match the extension of the PBI. And then when the flow channel diminishes in longitude, the PBI also diminishes in longitude again. Okay, so flow burst, PBI begins to extend westward, and you can see this flow channel is now getting much wider. The flow channel intensifies and the PBI intensifies again. And you can see this flow channel begin to shrink again in longitude, also become weaker. And the PBI also diminishes and becomes weaker at the same time. So this tells us that the azimuthal extent of the PBIs correspond to the width of the polar cap flow channel coming in. And again, relating this to the magnetotail, this is telling us that the width of that inflow channel triggering reconnection is roughly equal to the spatial extent of the X-line. For our second event, we have a storm time event. So in the geomagnetic indices plot, we have a very strong solar wind driving main phase of the geomagnetic storm. And we also have a lot of auroral activity and substorm activity occurring as well. In this event, you'll see multiple PBIs and streamers breaking off the poleward boundary. This line here roughly indicates the poleward boundary. Typically in this latitude range, the poleward boundary would not be this low, but because it's a storm time event, the whole auroral oval has shifted equatorward. So this is the poleward boundary here, and the equatorward boundary is somewhere outside of the field of view. So you'll see multiple PBIs, one around midnight and one duskward here. And each of those PBIs are going to be associated with its own polar cap flow channel. So the first PBI will occur on the dusk side here. We get this nice flow channel coming in to this PBI, which turns into a streamer and moves equatorward. We get another flow burst and another PBI on the dusk side. And now if we watch the midnight side simultaneously, we get this flow channel forming there. There's the flow burst, there's the PBI, and this is all happening at the same time we're getting the PBIs and flow burst dustward. So this tells us that you can have multiple inflow channels in the tail, triggering multiple reconnection X lines. And for our third event, we are looking at an eastward moving PBI that formed in the dawn convection cell rather than the dusk convection cell. This was a pre-substorm PBI, so you can see a substorm occurred just after the timestamps of this video here. And again, what you'll see is a flow channel coming in, triggering a PBI. And then the PBI is going to move eastward along with the eastward convection of the counterclockwise dawn convection cell. So there's already enhanced flows and some enhanced activity going on prior to this specific PBI, but there's our PBI there. And it just drifts eastward along with the eastward moving flows. And then it spreads across the entire field of view, gearing up for the substorm onset. So here's our enhanced flows. And after a flow burst, we get PBI there and drifting eastward. So because this occurs in the dawn convection cell, this is typically where we expect to see downward region 1 field-aligned currents rather than the upward field-aligned currents associated with auroral activity. So in order to investigate this a little bit further, we actually plotted the magnetic field vectors from Ampere. And we see that there's a small scale upward field-aligned current around the same latitude as this PBI here. So we should likely see a small scale clockwise flow shear around this PBI, as you would expect from an upward field-aligned current, but it might just be too small for even our convection resolution to capture, or we do have some lack of echoes right around the PBI location. So these observations differ from previous results. Previous results placed this PBI at the equatorward edge of this dawn convection cycle, this eastward flow here. And this just tells us really that when you have these PBIs on the dawn side, that the currents and the physics involved is much more complicated than we might think. And we do need to investigate those a little bit more. So just to summarize the PBIs so that they don't get lost by the end of the talk, in all of the events we saw PBIs preceded by flow bursts. Again, this is evidence that the tail reconnection is being driven by inflow. The events showed that the flow channels can modify the spatial extent. In event 1, we saw the westward extension along with the westward extension of the flows. It can modify the number. We saw 2 inflow channels and 2 PBIs, and the movement of PBIs. We saw the eastward moving PBI along with the eastward moving flows. And so that is to say that the magnetotail reconnection that is associated with the PBIs is a critical piece of the substorms. So we do need to continue to study the relationship between these flow channels and the PBIs, which show a clear correlation or a clear relationship between the two. Okay, moving on to our substorms, I'm going to show 2 substorms that occurred on the same night and do a deep dive into their onsets and their expansions. So the first one we're going to look at is the first substorm on 2023, March 17th. In this video, you'll see flow channels that form in the polar cap around 10 minutes prior to onset. And then these flow channels will reach towards the growth phase arc. You can already kind of see the growth phase arc in this capture here before I start the video. And once the flows reach that onset arc, they will trigger onset. So here's our flow channel already forming, coming in from the polar cap. They reach towards onset and trigger onset there. You can find onset by that brightening of the auroral oval or brightening of the arc. And then when the flows kind of move westward azimuthally, the onset also expands westward. So you can see this onset starting to take up more space in the westward direction as the flows don't just come into the original onset location, but also come in on the west side as well. So just one more time. We have our flow channel coming in there and our onset. So we're clearly seeing these flow channels coming into the onset region. To look a little more closely, we could use kiograms. So kiograms are longitudinal cuts of the all-sky image data. And we take the kilogram of the Rankine camera and the Rabbit Lake camera. Those are the two different cameras used in that video. And then we look at the equatorward velocity or southward velocity from the high resolution velocity maps taken at the same longitudinal cuts of these two respective cameras. Onset can be seen as, again, the brightening of the auroral oval here. And in both cameras, you see these equatorward flows reaching towards the onset latitude for both of them. So both of them see these, these flow channels coming in and triggering onset. Looking at the second onset, our first substorm was over in these two cameras over here. The next substorm is going to be way over here in the Ionospheric camera, so a different location. And you'll see that this flow channel actually bifurcates from the original flow channel, from the original substorm, and is going to move westward towards this second onset location. So you can see the original flow channel here. That flow channel is bifurcating towards onset. You have some pseudo breakup activity. It quiets again. This onset to flow channel intensifies, and then we get our onset. So there's pseudo breakup activity not related to the substorm. This flow channel starts to come in, and once this flow channel intensifies, right there, then we get our onset. Now there is a gap here between the flow channel kind of in the polar cap and this auroral zone here. However, as I mentioned before, the first step of this sequence is the PBI, so those flows coming in from the polar cap. So we do see these enhancements of the flow channels prior to the onset, so we're assuming that some steps happen in between there, but this is the triggering of the start of the sequence, the reconnection before the onset here. So regardless, we're still seeing these flow channels in the polar cap kind of influencing the direction of the onset, where originally the onset was over on the near midnight side over here, and then once this flow channel bifurcates towards the Ionospheric camera, we get onset over there instead. And again, looking at the kiograms of this event, we have onset marked by this line here. And again, we don't have the flows in the auroral region here, but we do see these equatorward flows coming in from the polar cap prior to onset. And we see the enhancement of the equatorward flows at the substorm region during the substorm. So that's a sneak peek of the expansion phase for later. So going into the first expansion, what we'll see, so first onset, second onset, going back to the first substorm now. What you see is flows continuing into the surge region as the substorm expands. And when the flows cease, the substorm expansion also ceases. And then when we get a re-intensification of the flows, the surge develops again and begins to expand. So we'll show our onset again there. And this substorm has a quite lengthy time between onset and expansion, so there'll be a little bit of nothing for a while. And then we see our flows start to intensify. A surge develops right there. And then these flows intensify more into the expansion region. There's kind of our maximum expansion point. And then when the flows intensify again, like they are now, then we get another surge development. So each step of this expansion is seeing an enhancement of the flows. So again, going back to our onset there, a little bit of nothing, while you wait for the expansion phase to start. Flows start to intensify into the expansion region. They kind of die down a little bit, expansion stops a little bit. Flows intensify, you get a big expansion. Flows diminish, expansion diminishes. And then you get this intensification of the flows again and a re-intensification of the substorm expansion phase. We see kind of a similar story for the second expansion. So again, that's right after our onset. We have these very intense flows coming into the expansion region and enhancing the expansion phase. The expansion diminishes a little bit and then re-intensifies again. So again, we're seeing a stepwise like expansion phase. Each activation correlated with the intensification of these flow channels. And then at the end of the substorm here, you can see that the substorm activity has ceased and our flow channels are completely quiet again. So the duration of the substorm may also be related to these persistence of the flow channels. You also may have noticed that one of these substorms was much bigger than the other. So the second substorm was much more expansive. We can also potentially correlate those to the width of the incoming flow channels. So the first substorm is on the top panels here. This is the top left panel is the start of the expansion phase, and then the top right panel is the middle of the expansion phase for the first substorm. And then the bottom left panel is the start of the expansion phase for the second substorm. Bottom right is the middle of expansion for the second substorm. And you can see that the width of the total expansion phase can roughly be correlated to the width of the incoming flow channel again. So just drawing some rough lines here, estimating the widths of the expansion and the flow channels. For the first substorm, we have an overall expansion width of around 2 MLT, and then a flow channel width also of around 2 MLT. The second substorm is a little bit harder to judge because we can tell that it goes a little bit off camera here. At the same time, we also don't have any radar data to the west here, so we also might be missing some more width of the flow channel. But we also see a more expansive substorm with around 3.5 MLT or greater, and then again a flow channel width of greater than 2 MLT. Again, looking at this in the kilograms, these are now the kilograms of the full substorm, not just the onset. The left panel is the first substorm, the right panel is the second substorm, just using the Rabbit Lake and Inuvik cameras. And overall, you can see that the first substorm was also not as expansive in the latitudinal expansion. So the first substorm only had a latitudinal or poleward expansion of around 3 degrees, whereas the second substorm had an expansion of almost 10 degrees. And you can see these two equatorward flow figures, kilograms, are in the same color scale, so you can very clearly see that the flows were much more intense for the second substorm. So these weaker polar cap flows may be associated with a less expansive substorm as well. And we also can see the stepwise like expansion, especially in the second substorm here. You can see the expansion starts to diminish around 9 UT and then picks back up again. And you can see this stepwise like enhancement of the equatorward flow channels as well. You get a clear enhancement here and then an enhancement here. And in both substorms, you get a very clear drop off of the equatorward flows or flow channels at the end of the substorm. So these flows may also be controlling the duration as well. Okay, to put that all together, since it was broken up, here is the full video of the two substorms. So again, we'll get our first onset over on the near midnight side over here. There's our onset. And then we'll get our expansion. And again, the flows extended towards the onset region for the first substorm and for the second substorm. And you'll see this first expansion going now. These expansions are step-like with activations of the expansion associated with the intensification of the flow channels. And there's about the end of our first substorm. And you get some quiet time for about an hour between the two substorms. And the second substorm is about to start. Here's the pseudo breakup that I mentioned earlier. Here's that flow channel bifurcating towards the onset region. There's onset for the second substorm, intense flows coming in, potentially driving this expansion phase. And then when those flows diminish, the expansion or substorm ceases. So again, the expansion size may also be correlated with this associated flow channel width, since the second substorm was more expansive and had more intense and a wider flow channel. Again, just to get a full picture of now the PBI to streamer to onset and expansion, we have this substorm on October 13th, 2023. In this video, you will see the flow channels coming in from the polar cap, triggering a PBI. This PBI will extend equatorward towards the onset arc. These flow channels will follow the PBI, come in across the auroral oval towards the growth phase and trigger a substorm. And then the expansion will continue with these intruding flow channels. So first in this video, there's a little bit of a PBI, but it diminishes. There's our flow channels coming in. The flow channels start to do some wonky sunward convection stuff, and then the flow channels continue again, triggering this PBI here. PBI begins to tilt, become more north-south aligned. Again, we're still getting these flow channels coming in, feeding this PBI. And then eventually you'll see the whole system move equatorward, as it is now. And you'll get a flow channel coming in across the center of the video here, right there, coming across, triggering onset. So it happens very quickly. Flow channel initiates there, comes across, triggers onset. So again, we're consistently seeing these flow channels come across, come down from the poleward boundary and trigger onset. And then again, we have a stepwise like expansion where we have more intense expansion during more intense flows. Whenever the flows start to diminish, the expansion starts to cease as well. So Using these new high-resolution flow observations, we show that the mesoscale flow channels play a crucial role in the initiation and development of magnetosphere-ionosphere coupling sequences, such as PBIs and substorms. We saw for the PBI events that the flow channels representing reconnection inflow can trigger multiple X lines and correlate with X line morphology, such as movement and spatial extent. And we also saw that flow channels preceded substorm onset in all of our events, which again, relating to the magnetotail, is delivering this low entropy plasma and triggering instability needed for substorm onset. And we also saw that flow channels may contribute to the azimuthal extent and the duration and intensity of substorm expansions as well. These are just a few case studies, so we're still looking at more statistical characterizations of all of these events. So yeah, thank you.
Do we have any questions for Steve?
Yes. So I'm wondering about the how you can quantify the uncertainties in your ambient data, or sorry, your super darn data pre spherical recurrence, and how you can quantify the uncertainties all the way through looking at things like flow channel width, which I think your results kind of depend a lot on. For example, I don't know a ton about super darn, but I imagine that if you pick like a point, one of those velocity vectors, that is only covered by 1 or 2 ISR fields, then you could be missing a component of the velocity. Is that right?
I don't know if you're missing a component of the velocity, because it.
So I mean, the ISR measures like the flow along the beam direction.
Yeah.
So I mean, if you have 2 beams that are kind of like facing each other, then you might get a component of velocity that you don't measure kind of perpendicular to those.
Yeah, so the yes and no, the spherical elementary current systems method, instead of doing like a triangulation where you need like 3 different points to get or 2 different points to get the 2D flows, like I said, it places those 2-dimensional poles of flow, and so you're placing a pole of flow and seeing which line of sight flows around it kind of match your projected vector of flow, if that makes sense. So yeah.
But then so the current systems was originally developed for magnetometer data, right? And in that case, every observation is from like a magnetometer, and you know the full magnetic vector. In this case, I'm wondering if you really have such high confidence about the actual observed velocity vector. And if you don't, then I'm wondering like how that.
Yeah, so we for these, like I said, these kind of denser areas and these thicker arrows are regions where we do have observations, so those regions can be trusted. Regions that like I wouldn't trust, for example, is this area here. These thinner arrows mean that that's just the solution being projected onto that area, but there's not actually observations there. So anything with these thicker arrows are places where we actually have observations, and we trust those results.
Okay.
In terms of your first question, propagating the error, there is some error in the location of the like echo return or location of the observation where it comes down to, but I don't think that error propagation matters too much for this study, and also that propagation of error is just assumed kind of a blanket, like 100 kilometers or something, and it's not propagated throughout the solution.
Okay.
Yeah.
A very simple question. I mean, what you're showing here, is that only the measurements, or is it already measurements fitted? I mean, normally what the super people show is, I mean, the fit of the data.
Yeah, this is the fit using the spherical elementary current systems.
Everywhere.
Yeah.
Everywhere. Even where you don't have observations.
Yeah, so,
Okay,
yeah, so we sample the solution, the spherical elementary current systems makes the solution based on, this field where we have echoes,
yeah.
and then we sample the solution and we know which areas
I mean,
don't.
based on the previous comment, I mean, you should be able to derive, I mean, an error measure, for example, how many, I mean, each of these arrows, how many super downs actually contribute to that? I mean, it could be a single one or it could be five.
Yeah.
Where they overlap, you could even, if it's, let's say it's two, and as you said, they're looking in against each other, I mean, you still have a very limited constraint, so.
Yeah,
So one should really make a map, of the confidence, that
Yeah.
maybe what underlies, I mean, the errors themselves.
yeah, I mean, there are errors in, so this method was validated against DMSP for the, validation of the method. And then there are also error calculations you can do against the line of sight, just the data. And those errors were.
So what do you mean by validation? I mean, the MSP flies through occasionally.
Yeah,
Okay, so you get some vectors there, I mean,
yeah.
how do you use that to validate? I mean, I don't understand that.
Well, I mean, it was just used for a few case studies when this method was being developed, but in terms of a case by case basis, these spherical elementary current systems, the high resolution fits, they can be validated against the line of sight data.
So there's a paper by Bob Funk, which is,
Yeah.
I don't know, 10, 15 years old. But he actually looked at, he's completely independent of, I mean, the DMSP people and the Supergun people. He compared and he found out that 80% of the time, not even the direction of the flow was correct. I mean, correct in the sense that they coincided, so,
Yeah.
because there's no ground truth. I mean, nobody measures the ground truth.
Mhm.
So I find that a very valid concern. Now I have a different question. Has anybody ever observed in the tail how a flow channel triggers reconnection?
It's been simulated, but
I'm a simulator. I can simulate a lot of things.
yeah.
Yeah, okay. No, I'm just asking because there are 10 years of MMS data now. There are 20 years of MS data, in the tail. There are plenty of data there, And it's just find it curious, that nobody ever has shown data that say, okay, here we see the flow channel, and then bang, and reconnects. I've never seen that.
Mhm.
And they're well equipped. I mean, they have the electric field measurements, they have
Yeah.
the plasma measurements, they have everything, And on top of that, I mean, there are more than one satellite, so that well, MMS is very closely spaced, but the three FEMS, they're often spaced enough, that one should be able to find cases where one actually sees the flows and then the other one sees the reconnection.
Yeah.
Never seen that.
Yeah, I don't know too much about MMS results. I just know that, like I said, for 90% of hundreds of PBIs, we see a flow channel associated with the PBI. So.
Okay, which brings me to another question. I mean, you did not mention the work by Stephen Mende. I mean, Stephen Mende looked at the same data that way back. I mean, Larry Lyons and Toshi looked at and came to the conclusion that this is all coincidence.
Mm-hmm.
So how do you respond to that?
I don't know.
Okay.
I'm just going off of the results that I have. Yeah, what I've seen.
Oh.
I have a somewhat naive question. On slide 24, I think it was, there's an initial brightening in the westward ASI. Is that just from like sunset or early on in the sea?
24.
Yeah, it starts off all black and then suddenly on one frame it
Yes.
saturates. Is that just
That is the Inuvic camera turning on.
got it? Okay.
So yeah. So it's March, so it's getting into spring, summertime where we don't have as much time with the ASI, so it just doesn't turn on until later in the night. Yeah.
Thanks.
In the October video, the very last one we watched, it looked like there was a pretty big flow channel to the right before the one that came down.
Yeah.
Do you have thoughts on why certain flow channels actually cause it to happen and other ones are just there and don't do anything?
Yeah, that's a good question. It's something we still have to look at, especially because, see this flow channel on the right, it kind of has that harangue type flow, so it looks like it's that large scale convection flow there, whereas it's only this individual streamer-like mesoscale flow that comes in and triggers the onset. There's a nice snapshot there. But no, we're still, I mean, like I said, we weren't able to look at this data with flows until this year. So it's still something that we're actively looking at, why we get some flows triggering onset and why we don't, and how often they even show up. Yeah.
Any other questions for our speaker? With that, we'll thank our speaker one more time.